We're going to play some more with exponential functions, exponential equations. Here we're going to start off with carbon dating. So carbon 14 over time shifts over to carbon 12, and by looking at the percent of carbon 14 in an old object, we can estimate how old it is. So we have this equation right here where we get about 88% of the carbon 14 remaining every 1,000 years. So T here is in thousands of years. It's important to keep in mind. So if I make a table for what this is telling me here, that in the beginning, something has 1 or 100% of its carbon 14. And then over time, we lose about, what's that, 11, 12% of the carbon 14. So that 1,000 years later, if I plug in 1 for 1,000 there, I'll find that I have 0.8861 or 88.61% of the carbon 14 that was originally there is remaining in there. And so for 2,000 years later, that's another 1,000 years. I can calculate this amount by taking my base and raising it to the second power. And then we can go and do that again for the fourth power for 4,000 years, because again, T here is measured in thousands of years for this equation. So, fourth, and so on. So I'm going to whip out a calculator to help calculate some of these values to see what's happening to the sixth power. Spreadsheet would be a good tool for this. So I'm keeping track of thousands of years here, and T is thousands of years, so 1,000 would be a 1 for T, and 2,000 would be a 2 for T, and so on. So over here, I can calculate the amount by saying base amount, 0.8861, raised to the power, how many groups of 1,000? So 2,000 would be 2 groups of 1,000. So I can say after 2,000 years, it should have about 78, 79% of its carbon 14 left. And I can just keep repeating that idea. And notice that this is pretty much the same formula I typed above by just typing my base and clicking on the cell to the left. So alternatively, I could just fill that down and it will automatically calculate based on the right exponent there. So here I can see 6,000 years later, I have about 48%, which is just under half. So 6,000 years is about what we would call the half-life. So half-life, carbon 14 is about 6,000 years. It's actually a little less than that. So it turns out if you look it up, the half-life turns out to be about 5,730 years. I get half of what I started with. So every time I look at another 5,730 years later, I get half of what I had before. So take the formula here, I take the number above and add 5,730 because I just want to look at that chunk of time. And another 5,730 years will be a total of 11,460, and I should get half again. So the amount above divided by 2, so 25%. And then I can just keep repeating that idea. Take that number above, add another 5,730 years to it, and that should give me half again of what I had before. So half of 25% is about 12.5%. And again, we can, since I typed formulas for each of these that depend on the number above, I can just fill them both down. So this is again adding that 5,730 to the previous number of years. So another half-life later, half of 12% is about 6%. So we can count by the half-life. And what you can see here is, it's pretty slow the way carbon 14 decays into carbon 12. And so we're jumping into like geologic time, which is really hard to grasp for us humans since we do not live anywhere near these ranges of time that go by. So to deal with big and small numbers, we often, instead of talking about the actual number, we look at the power of 10 because these numbers get too big too fast. So that's going to be another theme for this lesson. All right, let's take this carbon-14 thing a little bit farther, and let's see if we can figure out how long it'll be until an object has 20% of the carbon-14 started with. So 20% as a decimal would be 0.2, because percent means divide by 100. So I want to know when my formula, 0.8861 to the t thousands of years, is equal to 20% or 0.2. So to solve this, I need logarithms, which we've been getting better at, hopefully. So I would take a log of both sides. So the log of 0.8861 t has to equal the log of the other side, 0.2. So just like we can divide both sides, we can take a log of both sides. Now the power of taking a log is, one of the properties is the exponent pops out. So now I get t times this log of 0.8861 equals the log of 0.2. And this is just a number right here. I can plug it into my calculator and I can get a value. Now, if I do that now, I'm going to introduce some extra rounding errors, so I'd rather not, but I ask my calculator what is the log of 0.8861. The calculator says, hey, it's about negative 0.05-ish. And I could just write that down and continue, but I'm going to avoid that extra rounding error and just say, well, you know, this is just a number. I can divide by it to get rid of that multiplication there. I'm going to divide both sides by the log of 0.8861. And although one is sometimes tempted to cancel those words log, they are inseparable from their numbers. So just like my name is Gary Parker, Gary and Parker are pretty much joined together for me. I cannot separate the log from the 0.02 or the log from the 0.86. What I can do, however, is on this side note that a number divided by itself is 1. 1 times t is t, so t must be that. And now it's time for my calculator. So ask the calculator, what is the log of 0.2, close the log, and then divide by the log of 0.8861. I get it's about 13.31-ish, depending on how many decimals we need. So I didn't introduce any rounding error here. Now, if I had gone by the other route where I rounded and then divided, my answer would be a little bit off. So I could have said that this log of 0.8861, my calculator said that was about negative 0.05. And then I could divide by negative 0.05. But again, that's a rounded value, so it could introduce too much rounding error. And so t is about also equal to that. Now, before I calculate that, let's write down what this other value was. Let's take it to 4 decimal places, 3093. So calculator says that's about 13.3093. We'll get to that, what it means in a sec. Double check the rounding error I might have introduced. I take the log of 0.2 divided by negative 0.05, and I get 13.979. So again, you got to be careful with rounding too early in calculations. It can introduce a bunch of error. So I'm going to go with the 13.3-ish number. It's a little more exact. All right, so it is t. What is t again? T, remember, is thousands of years. So that is 13.3 thousand years until an object reaches 20% of its carbon-14, is what we just calculated there. So if if we want to disstate that in actual years instead of thousands of years, I could say that the actual number of years, 1,000 would be 3 zeros. So move that decimal 1, 2, 3. So 13309 would be the actual number of years, 13,309. Ooh, I'm a little crazy there. All right, so carbon dating. Sometimes, again, we have to deal with big numbers, and logarithms can help. And so here's another example. When we're looking at big distances, it's pretty far from like Earth to Mars, for example, even though on this scale up here, it looks like they're right next to each other, but that's just in comparison to, say, Neptune being so damn far away. It's hard to see the vastness of Earth versus Mars. If Earth was really close to Mars, right, we could go check it out and do stuff there, but even the moon is pretty darn far away. So sometimes to compare things that are just so vastly different, like the distance from Earth to the sun versus the distance of Neptune to the sun, instead of looking at the actual linear scale, what we do instead is look at the power of 10. So how do we get from this scale up top to this scale down here? If you consider Neptune is about 4,500 million miles away. These are in millions, by the way. Important. Of miles, or no, these kilometers. Let's see, kilometers. Kilometers, sorry. Million kilometers. Millions of kilometers. There we go. I want to convert it to what's called a logarithmic scale, which needs a power of 10. So the question is, 4,500 is equal to 10 to what power? Well, power is a logarithm. So answering the question 10 to what power equals 4,500 would be the same as saying that power is a log, and we want the log of 4500. Just a few minutes. Okay. So we can ask the calculator what power of 10 that is. So let's see, calculator, log of 4500. Calculator says it's about 3.65 power. And if we look at the scale here, for Neptune, here is about 3.5 for a power of 10. Here is the fourth power of 10. So this would be 3.6, 3.7, 3.8, 3.9, and 4. So Neptune, I calculated, was 3.65-ish for the power of 10, which sits on that scale. So here we're plotting the power of 10. And that allows us to see these things in a similar manner. So notice the spacing on the logarithmic scale, the spacing on the linear scale. These guys look all bunched together, but when we just look at the power of 10, we can kind of see them all together. Pluto is way off the chart on this linear one, but I can actually estimate it over here. So I'm going to try to do that next. So Pluto is right about there. Right. Let's clear some stuff out of the way here. Which power of 10 is that? Well, 3.5, 3.6, 3.7, 3.8, somewhere between 3.7 and 3.8, closer to 3.8. So I'm going to guess it's about the power of 3.77. So to get its actual distance, because that is the power, right, of 10, we would say, all right, well, what's 10 to 3.77? And open out our calculator again. What is 10 to the power of 3.77? And it's about 500, let's call it 5,900 million kilometers, or 5,900 million kilometers. So go back to desktop. So I think this is about 5,900. And again, that's millions of kilometers. Right, so that's pretty far out there. All right, that's it for now. I hope you found this informative and useful. Do good math. See you later.